Hello my friends, welcome to Sciencing Around. Again, happy sciencing, and now it's my second video for the atomic structure. As the previous video was quite long, I promised you that I will teach you the quantum numbers. Guys, please correct me. It's not quantum numbers. Quantum doesn't have any numbers. And it's study. I'm a virgin. Yes. So quantum number. Quantum number. Let's talk about quantum numbers. So let's science. Come on. So basically, what are quantum numbers? The quantum numbers are the actually the four numbers which tells us about the electrons, or which gives us the each and every biodata of the electron which revolves around the nucleus. Yes, which revolves around the nucleus. Each and every it's just like the biodata, like birth certificate, marriage certificate, and death certificate of the electron is given by the quantum numbers. Even the direction or spin of the electron, everything in quantum numbers. So let's get on with our first quantum number, that is the principal quantum number. And now guys, listen to me. You have to listen to me more rather than seeing, because here more thing is on listening and less thing is on seeing, because I have written very less and I know very more. So at first, what is principal quantum number? Principal quantum number, it is denoted by the letter N. Sorry for my small handwriting. It is denoted by the N number. And principal quantum number tells us, or the principal quantum number determines the size and the energy of the orbital. Size and the energy of the orbital. I hope you know about the orbitals. SPDF, G orbital, which is not yet discovered. So SPDF are the orbitals. It tells us about the size and energy of the orbital. And N, that is principal quantum number, can have values 1, 2, 3, etc. And let me tell you, I hope you know about the shells, KLMN shells. I hope you know that thing, that whole shitty thing, that is K L M, and these are the shells, that is KLMN 2, 8, 18, 32, and all that. In your last grade you must have studied it. And now KLMN. For the KLMN, the principal quantum numbers are 1, 2, 3, and 4. That's the basic thing for you to understand. For KLMN, the principal quantum numbers are 1, 2, 3, and 4. You will know the principal quantum number very accurately and very, very brilliantly when I make the video for the chemical bonding, the first topic of inorganic chemistry. I'll make it very soon. But right now, you just have to remember that it tells us about the size and energy of the orbital. I hope this page is over. Let's get on to our next page, that is azimuthal quantum number, which is denoted by the letter L. Now guys, listen to me. I'm gonna tell something. As you can see, here it is written for principal quantum number N. Alright, let me zoom that thing. For the principal quantum number Fn, the value of azimuthal quantum number equals to 0 to n minus 1. Did you read that? The value of azimuthal quantum number would be 0 to n minus 1 for the principal quantum number L. That is for 0, 1, 2, 3, 4, 5. If the subshells, you know about the subshells, every shell has one or more than subshells. And the azimuthal quantum number tells us about the three-dimensional shape of the orbital. Three-dimensional shape deals with azimuthal quantum numbers. So for subshell SPDF G, H, these two are shit, fuck. So for SPDF 0, 1, 2, 3, 4, 5, I don't know why. So now let me tell you about the principal quantum number, azimuthal quantum number from n minus 1, the one number before of the principal quantum number, and deals about the three-dimensional shape of the orbitals. Now this is the second type of the quantum number. Third is the magnetic quantum number. Magnetic quantum number. Now guys, listen to me. Here I've written, don't read it right now, you won't understand. For a given value of azimuthal quantum number, the magnetic quantum number can take values of minus L to plus L. That is 12 plus 1 total, including 0. So the total possible values are 12 plus 1. Now here it is an example. If this is the azimuthal quantum number, which is 1 1 is the azimuthal quantum number, L equals 1. Then m can take the values -1, 0, 1, and so on. No, not like and so on. I didn't write that. So now just like suppose L equals 3, then m, which is magnetic quantum number, can equal to -3, -2, -1, 0, 1, 2, and then 3 possible values. That is 2n plus 1, that is 2 into 3 plus 1, that is 7, 1, 2, 3, 4, 5, 6, 7, 7. And the last thing comes, that is spin angular momentum. What the heck, right? It's not spin angular momentum, come on. It's spin quantum number. It's the spin quantum number, the spin angular momentum, and the spin quantum number that is under root of s into s plus 1. Spin quantum number can be denoted by s. So under root of s into s plus 1 h upon 2 pi. You don't have to remember this thing because it's not quite so important. Forget that. Just spin quantum number. Now listen to me. An electron spins around its own axis. Of course you know. It has besides charge and mass. Yes, electron has charge, mass of 9.3 to 10 power minus 31 grams or kg or something. Spin angular momentum is a vector quantity, and spin angular momentum has two orientations relatively to chosen axis, where plus 1 by 2 or minus 1 by 2. There are only two possible spins of electron, that is plus 1 by 2 or minus 1 by 2. Now about electronic configuration, let me tell you in some other thing, that is the electrons are, these are the window looking like things you can see. The Pauli's exclusion principle, I don't know why did I write this right now. Now just for atomic structure sake, let me tell you that Pauli's exclusion principle, these are the windows where you have to fill maximum of 2 electrons of opposite spins. Someone named Pauli told us that no electron can be filled in a single window of similar spins, and in p orbital we have 1, 2, 3, 4, 5, 6, as the limit of p orbital is 6 electrons. Hund's rule states that if the window is empty, then we cannot place 2 electrons in the same window. Alright, I hope you must know that. Then this won't come, this would come like this. If a window remains empty, then no 2 electrons or no electron can be fitted in some other window where there is already an electron. That's it. And now magnetic moment. Magnetic moment is very important. The moment of, what do we say, the magnetic moment in magnetism, you must have studied at NIA. In atomic structure, magnetic moment equals under root of n into n plus 2 Bohr magneton. Bohr magneton, let me tell. It's Bohr magneton. Again, that's silly Neil Bohr again. Bohr magneton. And what is n? N is the number of unpaired electrons. That is, if I take any elements, suppose I take Cu2 plus, this is the unpaired electron, 2 plus, n equals to 2. Therefore magnetic moment equals under root of 2 into 2 plus 2 equals under root of 8, some shitty value. Now guys, now I'm gonna take the plain page, and now I'm gonna explain you the orientations of the subshells, or what do you say, the orientations and the shapes of the orbits. So let's get on. So guys, let's get on with the shapes of different orbitals. Now let's take first s orbital. S orbital. S orbital is a sphere. Now to be very frank, let us draw some axes. Hope you can see that thing. It's x-axis, it's y-axis, and it's so-called z-axis, a 3-dimensional space. Then s orbital is a sphere. I don't know whether its center is at origin. No, its center, S is as a sphere, simple sphere. I don't even need to draw an axis because it's simply sphere. Come on guys, it's just a sphere, 3-dimensionally spread. It has its direction in x, direction in y, and direction in z. I think no need. Come on now, p orbital now. In play block you'll learn about p orbitals. P orbitals have many shapes, and here we have to draw the axis. Yes, we have to. Now let's take px. Px is the first type, as its name says. Again, I'm gonna draw the axis. That is, this is y-axis, this is x-axis, and this is z-axis. Px orbital, it has the orientation like this. See, like an infinity thing, like this. Yup. It's totally spread in the x plane, only x plane. So it's called as px orbital. Simply that with py orbital. See, py, it is x, it is y minus y plus, then py is like this. See, 8. This is the p orbital. Means it is an orbital. Inside we can find the electrons, like 3 to 4 electrons in the p orbital. And now another thing, that is pz, 3-dimensional thing again. X-axis, y-axis, z plus, z minus, 3-dimensional space. Pz is infinity thing, that is the whole thing spread in the z-axis. These all things are px, py, and pz. And now let's get on to d orbitals. Now d orbital needs a plane. Now let's get on. Let's move on. Come on. So it's d orbital. What the fuck is d orbital? Now let's see. It needs a plane. Not aeroplane, sorry, plane. It needs a fucking plane. So now first we can say dxy. I'm not gonna explain much because this video is still getting quite long. I again want to say I don't want to bore you guys, so it's y, it's x, or let it be y, let it be x. This is y-axis, this is x-axis. Let's spread this thing. Then d orbital is the 2 p orbitals having configuration like this. A flower. dx, dxy. Simple is dyz, yz, then dyz. If this is x, this is z, then dxz. And only one orbital which I have to say is dx square minus y square. It is dx square minus y square. Yes. In this thing, dx square minus y square, see, this is y, this is x, then it is like this. See, the petals, the axis, the normals of the petals are perpendicular to the axis. Here it is like this, and the x square minus y square is like this. So the s, p and d orbitals were very same. Now I don't need to tell about f orbitals because I didn't get information. It was not in books, it was not in portion, so no need of f orbitals. But these three were really very important. So thank you guys for watching. I hope you should end this video right here. This video is still going quite long, and if you like this video, if you think this video is quite informative, then please press that like button, subscribe my channel for more, and please comment whether you like this video or don't like. If you don't like, please tell me what the hell should I improve to meet your needs. Yeah, because I would like to earn your subscription rather than just begging. So please tell me what was wrong that I should improve. And if you like this, if you had no complaint, then please like and subscribe my video. It would be so helpful to me. It would really encourage me. And thank you for watching. See you soon. Happy sciencing and hope you learned something.